Good morning, my name is Chiara Rossi, and I am a PhD student working at AIMS at the Vrije Universiteit Brussels. Today I will present the first work of my PhD, which consists in a comprehensive network analysis of the brain dynamics underlying working memory. As we know, working memory is that cognitive function that allows us to remember an item and then recall it just after a few seconds. But how does the brain perform this cognitive function? What does the brain dynamics look like? So far we know that the brain recruits large-scale brain networks and that the brain regions involved in these networks communicate and synchronize using different brain rhythms, hence alpha, theta, and so on. Also, these networks wax and wane at milliseconds timescale. My former colleague, Lars Kosters, has conducted a detailed and thorough analysis of the brain dynamics underlying working memory. And he investigated an MEG dataset that was acquired during an MBAC test. The strength of his work regarded the high temporal resolution of investigation thanks to the MEG data. But at the same time, the limitations regarded the signal analysis technique that he applied. He investigated the data using an event-related field analysis, which, as we know, does not help providing insight in the brain waves when applied to MEG data. And then he also used a time frequency analysis. This carries a lot of information that is difficult to interpret and to integrate. Additionally, the network information is completely neglected. So starting from this investigation, we decided to move forward, and we decided to conduct network analysis on the same data set. We chose to apply the time delay embedded hidden Markov model, which is an unsupervised learning model that was already applied to conduct network analysis on MEG data. Here, I report the work by Professor Vidaure on resting state data, where we see a transient state that activates throughout the whole recording. And the state is characterized by spatial map that is described by the power spectral density distribution across the brain and the phase coupling network that is the phase coherence across regions. The same model was also applied already to analyze MEG task data by Professor Quinn. And the only difference with resting state data is that we can take the temporal course of the state, so the probability of activation of every state along the whole recording, and epoch it with respect to the task, information. In this way, we see what is the pattern of activation of every state throughout the epoch. So, by applying the time delay embedded hidden Markov model to analyze MEG data, we aim at decoding the temporal, spectral, and spatial dimension of the brain networks that underlie working memory. Also, we try to do so by conducting a data-driven analysis with a very high temporal resolution. As I mentioned, we use MEG data, high temporal resolution, MEG data from 38 healthy subjects that were acquired during MBAC task. The MBAC task is a widely used working memory task that consists in showing a sequence of letters, and every subject has to respond to a target letter. The letter is the letter X for the 0 back condition. For the 1 back condition, the letter is every letter that is identical to the one just shown before. And for the 2 back condition, the target letter is the one that is identical to the letter shown 2 times before. After acquiring the data, we pre-process them using the OSL software. I want to mention that we source reconstructed the data using a beamformer, and we parcel the data using 42 parcellation, 42 regions parcellation. Then we apply the HMM model to infer 6 brain states. Every state will be described by a phase map, again, the mean power spectral density distribution over the brain, the connectivity map, so the phase coherence across regions, and the every state will also be described in the time domain. In the time domain, we applied an ERF analysis by GLM model with a GLM model. And here I propose the constant regressor of this analysis, where we see the activity that is common to all the paradigm conditions. Interesting, we see that 4 states are significantly activated or deactivated throughout the epoch. And I will describe 3 of them, which we defined as task specific. The first state that activates is between 200 and 400 milliseconds. And it is activated in every single paradigm condition. We observe that this state is characterized by a high power in the prefrontal regions and also in the posterior cingulate and precuneus. This power is focused in the low frequency range, hence the theta range. The connectivity map shows the same a network that involves frontal regions, and then it also connects to the posterior cingulate cortex. These connections occur in the theta frequency band. Regarding the role of this state, we associate this state, we interpret it as the executive control of the stimulus encoding because of the involved prefrontal regions and the early activation of the state. The second state deactivates significantly between 250 and 500 milliseconds and is characterized by a space map that shows a peak of alpha power in the occipital regions. The connectivity map also shows a network that involves occipital regions that synchronize in the alpha band. The sustained decrease in alpha power in the occipital regions likely reflects the letter processing in these regions as well, as the alpha power is again inhibitory. The last state that I propose is a state that activates between 250 and 600, 700 milliseconds, and is much more activated in target trials rather than distractor. As we see by the spatial map, it's characterized by broad frontal regions that whose power is focused in the beta band, and the connectivity map is much broader and involves frontal region as well as the sensory motor cortex and other parietal regions. Regarding the role, because of its the timing of activation, and because this state is engaged much more in target rather than distractor trials, we associate and we interpret this state as a manipulation and response selection state. This is also because the dorsolateral prefrontal cortex is involved. Here I propose an overview of the brain dynamics that we unraveled so far. First, I want to mention that the temporal window we are looking at is shorter than 1 second. So we have a great temporal resolution of analysis. Second, we have the appearance of 3 states with 3 different functions. First, we have a prefrontal state that works as executive control of stimulus encoding. Then we have the deactivation of the power network, the alpha power network in the occipital regions, reflecting the occipital letter processing. And last, we have an increase of beta power in the frontal regions that is associated with response selection. To conclude, we do provide a comprehensive description of the network dynamics underlying working memory, and we do so in a very high temporal resolution. I want to thank Professor Van Schepenen, who is my promoter, as well as all the members of AIMS